Good morning, good afternoon, and good evening, everyone. And welcome to the last day of this meeting to celebrate the science of Giorgio Parisi. So today we have three talks in the first session. The first talk is by Spenta Wadia from the ICTS, and he will talk about planar diagrams and the large N limit of theories with matrix degrees of freedom. Spenta, yeah.
Thank you very much, Abhishek. It's a great pleasure to speak at this meeting celebrating the science of Giorgio Parisi. I will basically give you a very brief summary of the important contribution of Parisi and collaborators to this the subject of planar diagrams and large N limit of gauge theories with matrix degrees of freedom. So let me start by mentioning that this is the paper I will basically base my talk on. It's a paper by Breza, Itzikson, Parisi, and Zubair. It's a rather fundamental paper in this area. And what I'll outline is the foundational role played by this paper in the development of the large N limit of matrix models, and especially non-abelian gauge theories. We will briefly review one, the historical context of this paper, two, the main results, and three, its conceptual impact on the development of string theory, and conclude with a possible answer to the mean field of a UN gauge theory at large N. So in the early 1970s were very exciting times in high energy physics because non-abelian gauge theories basically came to the center stage with the discovery of the unification of electromagnetic and weak forces, the discovery of scaling in high energy deep elastic scattering, and the discovery of asymptotic freedom of non-abelian gauge theories. And also the very mysterious fact that quarks, which are the constituents of the strongly interacting hadrons, are permanently confined in the hadrons. The other exciting development around that time was K.G. Wilson's proposed lattice gauge theory. He explicitly said at a meeting when he proposed this, and I was there, that violate Lorentz invariance, but not gauge invariance. And using his lattice gauge theory and the strong coupling expansion, he computed what is this famous Wilson loop that tells you about the energy per unit length between two confining quark particles. And the loop is sort of tiled with string bits. The other important development at that time, somehow looks very remote today, but it's amazing. So there were parallel developments from 1960s trying to understand the strong interactions in the subject that was called dual models and now is called string theory. So as you know, if you take a string and it moves in space-time, it traces out a world sheet. And those world sheets appeared in the dual resonance model. And this is a very beautiful and important works of Kikawa Sakitabi Rasoro on the KSV program, which led to this idea of dual diagrams, duality diagrams. And it is this, as you will see, led to the development of string-like Feynman diagrams in gauge theories by Hooft in 1974. So let me just flash the abstract of Hoft's paper. So he says a gauge theory with color gauge group UN and quarks having a color index running through from 1 to n is considered in the limit of n going to infinity with g square n fixed. The topological structure of the perturbation series in 1 upon n is identical to that of dual models, such that the number 1 upon n corresponds to the dual coupling constant. A mathematical framework is proposed to link these concepts of planar diagrams with the functional integrals of Gervais-Akita in 1973 and Mandelstam same year for the dual string. we'll see that, I don't know whether I'll have time to mention all this, that is 1 upon n essentially, or 1 upon n squared, is identified with the gravitational coupling constant in the ADS-CFT correspondence. We'll see it later on a little bit. In summary, UN gauge theories are related in some way with string theory, and this relationship seems manifest by reorganizing the perturbation theory in powers of 1 upon n and holding lambda, which is called the Hooft coupling, G square n fixed. Chi here is the Euler character of the Feynman diagram. This related in some way, we still don't understand it completely, though there is very interesting work recently by Gabadiel and Gopakumar on trying to understand the precise nature of this correspondence in the certain limit in which G square n really goes to 0. Okay, so just to flash a couple of pictures, these are Feynman diagrams of a gauge theory in the double line notation, these fat graphs, which were invented by Hooft. And these fat graphs sit very nicely on Riemann surfaces, actually, as I have mentioned over here. So, you know, if you have a fat graph that sits on a sphere, then there's no handles. So this type of graph sits on a sphere. This type of graph sits on a sphere, but it has a hole. And this type of graph sits on a sphere with a handle. You can convince yourself in some way or the other, in some personal way, you can convince yourself that what I'm saying is true, and it's really true. Okay, so in general, I mean, for example, if you take a vacuum graph, which has, you know, this is the bread and butter of high energy physicists, Feynman diagrams. You have index loops, you have propagators, you have vertices. When all of this is taken into account very carefully, then you find that the graphs can be organized. Actually, the perturbation series can be organized in powers of n to the power of the number of loops minus the number of propagators plus the number of vertices. And this number, L minus P plus B, turns out to be precisely, obviously, the faces of the graph minus the edges plus the vertices, and that's the famous Euler character. And since we are looking at just vacuum graphs, in this case, it is just 2 minus twice the number of handles on the sphere that you put, okay? And therefore, the vacuum energy, for example, has a famous genus expansion. So you have the n squared piece, which is the sphere piece. And then there's some function of the Hooft coupling lambda, and so on. This is of order 1, this is of order 1 upon n square, etc., etc. So you can organize the perturbation series always this way. And this is a very brilliant step, very brilliant. But how do you compute it? That's the main question. So this is the question which was attacked by Breza, Itzikson, Parisi, and Zubair in their very famous and fundamental paper. How do you compute this type of thing? So they did what good theoretical physicists do. They looked at simple soluble models. So here's the abstract of their paper, that we investigate the planar approximation to field theory through the limit of a large internal symmetry group, etc., etc. And this yields an alternative and powerful method to count planar diagrams. Results are presented for cubic and quartic vertices. I'll explain that. Some of which appear to be new. Quantum mechanics treated in this approximation is shown to be equivalent to a free Fermi gas. I will explain all these to you. These are very beautiful things. So BIPZ solved matrix models in 0 and 1 dimension. So they're basically a matrix, just a simple random matrix, or a matrix which is dependent on one parameter, which can be time, temperature, whatever, and made a connection with the old subject of random matrix theory, which was developed by Wishart in statistics and Wigner in nuclear physics. In doing so, they established some general principles of the large n limit for more complicated systems. In fact, this is what I will come to. What is the impact of this? So when you solve these type of soluble models, they teach you some general principles. And that's the main point I'll try to make a little bit. in a little bit. So in these models, we can exactly calculate E naught lambda. Okay. Now, I have just written out what they have done here. So let's look at the matrix model in D equal to 0 dimensions. Okay. So this is a partition function, and this is a integral of in the space of Hermitian matrices, which is actually a flat space. And this is some action which I will mention a bit later. And these are Hermitian matrices. The action is invariant under the action of the unitary group in n dimensions. So this measure is easily derived. It's very simple. All you need to know is the metric in the space of Hermitian matrices, which I said is a flat Euclidean space. And you then write down what is called the polar decomposition. You know, just like in 3 dimensions, you decompose the vector x into angles and the radial distance, and the radial distance is invariant under the rotation group. So this is exactly what it is. The eigenvalues are invariant under the unitary transformations, which are a symmetry of the problem, and the eigenvalues, which are the analogues of the radial coordinates, precisely satisfy this measure. And I have not written the angular part of the measure because I am going to restrict myself, because of the action being invariant in the unitary transformations, to UN invariance. And therefore you get an effective action. You get a Coulomb gas problem, basically. And then you write the Coulomb gas problem in terms of the eigenvalues and learn to solve this model. So this model actually can be solved maybe on a computer, I don't know, but the first thing to do is to do a hydrodynamic approximation. So introduce a hydrodynamic variable, which is the density variable, the density of eigenvalues, right? It's normalized and it's positive. And so you get the effective action written as a functional now of the density of eigenvalues, okay? And you can now write a partition function. There's a bit of a subtlety in this measure, which it's not important for us to leading order. And you look at the equations of motion of the effective action, and you get an equation like this. This is a typical equation which you solve using the Riemann-Hilbert method, and here is the solution. So they solve this problem, and because the eigenvalues have to be in a certain interval minus 2a to plus a and normalized to 1, you essentially get this important equation, which can be expanded in perturbation theory over here. So G equal to 0, for example, corresponds to Wigner's famous semicircle law. Okay, and then because you know this solution, you can compute correlation functions. You can compute, you can do many things actually. In fact, you notice there's a singularity here at G equal to minus 1 upon 48, and that singularity essentially, as they have shown very nicely, determines the radius of convergence of this planar perturbation series. But all those things I don't want to talk about here, except the main principles. So you can also compute correlation functions like this of invariant operators. And you notice one very, very, very important point. This can be either proved by diagrams or by the fact that there is a saddle point solution over here. Okay, so this is called large N factorization. So this is the first thing you realize actually, that there is a classical solution, that the problem is recast as a semi-classical problem in which Planck's constant plays the role of 1 upon n squared. And then you have this type of factorization because you're working with classical trajectories in the path integral. All right, for models in D equal to 1, the situation is even more beautiful. So you have a Lagrangian of a random Hermitian matrix, which is time dependent, and you solve the Schrödinger equation. The Schrödinger equation. How do you solve the Schrödinger equation? You have to find a formula for the Laplacian. That again is simple because we know the metric in the space of Hermitian matrices, and when all the calculations are done, and very, very beautifully, what you get essentially is the Laplacian is written in terms of this van der Monde antisymmetric function in the following way. Okay, and we can forget about this angular momentum terms because we are going to restrict ourselves to the quantum mechanics of UN invariant wave functions. I won't go into details of that, but then you just look at this problem, Schrödinger problem. You can now redefine the wave function from being completely symmetric because it is UN invariant. The residual while invariance tells you it is a symmetric function of the eigenvalues. And so you have a many fermion problem where the eigenvalues play the role of the positions of the fermions. And this problem has to be solved in a potential. Each fermion just separates out, moves in this potential, whatever V is. And then you can compute the ground state energy very easily if you know the phase space distribution function of this problem. And this is the single particle Hamiltonian. So I have just written down their solution, that the phase space distribution function is just this Heaviside theta function, that all the energies are below the Fermi level and is normalized to 1. And you can actually solve this problem and for any potential V of lambda. And this is the beautiful thing they did, actually. And the comment I just wanted to make is, if the potential has multi-trace operators, like some powers of like trace m square, then to leading order, just this is Hartree-Fock approximation. You can write this in terms of trace m square times the expectation value. And you have the same problem, but with more consistency conditions. So, sorry, let me get back to it. So what do the D equal to 0 and D equal to 1 matrix models, which were solved by Breza, Dixon, Parisi, and Zubair teach us? So there are 3 very important lessons which have had a very deep influence on this subject. And the first one is the importance of recasting the problem in terms of UN invariants. In this simple example, the invariants were just functions of the eigenvalues. Now, this is a very general lesson, as we will see a bit later, and it is a source of a lot of non-locality of the effective action in more general models. The second point is that the large N expansion written in terms of UN invariant variables becomes a semi-classical expansion in 1 upon n, where you identify n square with 1 upon h bar, and the path integral over the density of states, or the phase space density of states, is evaluated to leading order in n by a classical solution. And this was the first example of what people later called the large N master field. And the third point is that the expectation values of UN invariant operators factorize, and which is essentially equivalent to having a saddle point in the path integral. Okay, so BIPZ also inspired further explorations on unitary matrix models. I mean, people just started looking at how to apply these ideas to lattice case theories in low dimensions. And some work was done in that direction by looking at this unitary matrix integral, which is given here in the first paragraph. And it was solved to indicate that there is a large N phase transition in this unitary matrix model. There's a very simple and beautiful explanation of why it happens, but I don't have the time to go into it. So the same is true if you look at unitary matrix quantum mechanics. Just look at the Breza et al.'s work on Hermitian matrices and try to do it for unitary matrices, and you find something new and interesting, actually. And so a lot of this literature was collected in this reprint volume, which was edited with Edward Breza. And also there's a very beautiful textbook by Marcos Marino, which explains all of this stuff very nicely. Okay. Now, let me turn to another subject, actually. Many years later, after the late 80s, there was a revival of interest in matrix models again, because of its connection to two-dimensional quantum gravity. And so around 1990, these models were used in defining a theory of two-dimensional quantum gravity. Now, how do you do that? So I told you before that the Feynman diagrams are topologically Riemann surfaces, right? So you can put those diagrams on surfaces of a sphere with handle, etc., etc. Now what you do is you do this following trick, which I have drawn in this right-hand side over here, that you take, for example, the 4-gluon vertex over here, in double line notation, this fat graph, and write a dual diagram to this. The square is dual to this. If it was a 3-gluon vertex, it would be a triangle, etc., etc. Then what you do is take that Feynman diagram and look at it in terms of these dual squares over here. So you get some sort of a triangulation or a latticization of the two-dimensional surface. That was the idea. It's a very simple point, actually. I think it was due to people like Kazakov and Dhar and those people. And then what you would like to do is take the continuum limit, take this mesh to 0, and that could be done in a systematic way by what is called the double scaling limit, which is basically you are near the large n phase transition, and you scale your parameters in such a way that you get a good continuum surface. Okay, so now along these lines, if you look at the matrix model, which is time dependent, I mean, one Hermitian matrix which is time dependent, and is coupled to some matter fields. It's called C equal to 1 because that comes from conformal field theory. It's not important for this talk. And you have this same BIPZ matrix model with a certain potential. Now, as I said, you do a scaling of the parameters of the theory. And for example, what you get is you have to look near the hump of the potential where the Fermi level starts getting, you see the Fermi level over here, if it gets the bare Fermi level, I mean, gets near the hump of the potential, you have a large n phase transition. So what you do is you rescale variables actually by n, and I cannot explain all that detail, but all you get essentially, ultimately, is a problem of fermions moving in an inverted harmonic oscillator. And so originally, of course, you have to start with a bounded potential, but the wells of the potential just go away as n goes to infinity, and you're left with this type of potential problem. And then you study oscillations on the Fermi surface, and they were studied by several people. And those oscillations essentially consist of a scalar particle in 2 dimensions. That's the key point. In 2 dimensions, which satisfies this equation, which I have written at the bottom. And this equation, interestingly, coincides exactly with the equation satisfied by a certain massless excitation in 2-dimensional string theory. So in a sense, this is our first brush with holography, which I will come to a bit later. Okay, so this is a direct consequence of the work of Parisi and collaborators in matrix models. Okay, now many applications of matrix theory are there, and it's a very flowering subject. I just thought of showing you a slide from Satya Majumdar, whom many of you would know, comes from the statistical mechanics community in Paris, and he comes very often to our institute. And you see just see the landscape which random matrix theory addresses, large deviation theory, then permutation problems, Lattice gauge theory, all this amazing thing. And it's a very beautiful, very sort of informative article in Nature Physics, actually, which is a sort of a conversation with Satya. It gives you a certain perspective of the random matrix theory zoo. Okay, so now this is all about random matrix theories, but we have deviated actually. All beautiful things have happened. So the question still remains, what is the master field of large n gauge theories? Okay, this is amazing. So we began our talk with planar diagrams and learned from the work of BIPZ that one needs to find a set of equations that would compute the sum of planar diagrams in higher dimensional gauge theories. The answer to this question came from an extremely unexpected direction. And it's just deeply seated Yes.
Sorry, so you have your time is up, but you can take a couple of minutes, I think.
Yes. Yeah. Thank you so much. Actually, just 5 minutes, I will finish it.
Yeah.
I'll go very fast. Maybe you don't understand, but then you can see the slides. So it's deeply seated in the ideas of duality in string theory and supersymmetric field theories by Kikawa, Yamasaki, Font, Coedo, Lust, all these people, Sen, Witten, Seibert, etc. Very, very long drawn work in DNS dualities of string theory. That was about symmetry. Then there is the discovery of the new stuff of string theory. String theory has new stuff, which is different from gravitons. And this is the discovery of D-branes by Polchinski, actually. And that new stuff was used to model black holes. You engineer a black hole in terms of D-branes and see its geometry, and then it would compute in this very special cases. The black hole entropy is exactly equal to that which is given by Boltzmann's formula. So there was a deep connection between statistical mechanics and theory of gravity. And if you excite these black holes slightly, you can study the Hawking radiation. And all the formulas work out the same way as in gravity, as Hawking had shown us. Okay, now, what about the master field of gauge theory? So this is almost the last slide, I think. Putting all these insights together in 1996, Juan Maldacena proposed the ADS-CFT correspondence in which at large n and large lambda, the saddle point or the master field of a large n gauge theory, what is that, Abhishek?
I don't know, someone's...
Yeah, alarm is going, somebody's
alarm.
Okay, sorry, it was my alarm. And I was not cognizant. Sorry. Okay, what was I saying? So this is the amazing thing, that the classical solution actually is, it cannot be written in terms of gauge theory variables, but it is given by as a solution of Einstein's equations of general relativity in one higher dimension. Okay, and there are many tests of this correspondence. And here two matrix models have been useful. For example, the derivation of this famous and beautiful Gopakumar-Vafa duality was done using matrix models also by Marino in his Hooft lectures. And unitary matrix models have been also useful in the study of black holes. You can follow all this literature from the slides. I'll do one last thing because I have to make a connection with the statistical mechanics community that is listening to this. So we have the famous Sachdev-Ye-Kitaev model of n real fermions at this point interacting by random all-to-all interaction without a spin glass phase. Okay, it's engineered so that there is no spin glass phase. Now the low energy behavior of this theory is given by a Schwartzian, and the low energy what shall we say, Landau-Ginzburg parameter of this theory is essentially an element of the diffeomorphism group. Okay, diffeomorphism, that's a big word for essentially
I'm not sure I
a function of time or temperature. And the effective action basically is this famous Schwartzian. Now it turns out that this model is also holographically dual. The SYK model, which is a model of random systems, connects with a model of gravity. Now, here to random matrix theory has been very, very useful and prominent, and I just wanted to leave some references with you, and I'll leave you with a question. And the question is the following, that if you can add interactions to the SYK model so that one possibly can have a transition, a phase transition to a spin glass phase with lots and lots of minima, what would be the description of the dual gravity theory for this phase? I think this is an interesting question which perhaps people in the statistical physics community might be interested. Okay, so congratulations, Giorgio, again for your scientific journey, which is an inspiration. And thank you very much. And thanks to Abhishek, Chandan, Samriddhi, and Smarajit, and the ICTS for organizing this celebration of the work of Giorgio Parisi. And very sorry for this interruption. And yeah, that's the end of my talk. Thank you for listening.
Thanks a lot, Spenta, for this really wonderful talk.